Hello, and welcome to this second to last talk today about nobody puts Spark in the container. And let me actually start by clarifying what's meant by this title to get expectations right. So, who of you actually knows this reference? Show of hands is kind of hard to see, yeah, but there has some hands up. So it's from Dirty Dancing, and it's the scene where she's sitting in the corner, and actually, he isn't too happy with that. He comes and pulls her out, and it's supposed to be baby isn't sitting in the corner. She doesn't belong there. It's not so much about saying that Spark doesn't belong in a container, because it's running nicely in a container, but there might be some unexpected events happening, as for example, someone coming there and pulling her out of this corner. And this is actually what this talk is about. It's about how to decently run Spark, or in general, Java-based applications in a container, and basically which pitfalls there are to avoid. Maybe just to get a feeling for the audience, how many of you have experience with Docker or other container technologies so far? All right, that's quite a few. How many of you have experience with like the underlying layers, as for example, cgroups, namespaces, and what's going on there? Okay, that's less. I might have some slides which could be kind of boring for you, but I hope you still stay awake throughout this slide. It's going to become more interesting after those slides again. Actually, it was supposed to be Ken and myself. We both work at Mesosphere. Ken is a distributed applications engineer. That means he mostly works on applications as, for example, how to run Spark efficiently on Mesos, how to run Marathon efficiently on Mesos. And I myself, I'm a distributed systems engineer. The differentiator is that I work on the core Mesos project. And it's a C++ project. So you might ask yourself now, why do I care about running Spark in a container? And I promise this is like the only DCOS slide or the only product slide I'm going to have in here, but it kind of explains why I care about running Spark in a container. DCOS it's a distribution built around Apache Mesos. Apache Mesos, if you followed the keynote yesterday, it's actually been co-developed together with Spark at UC Berkeley at AmpLab. And it's an abstraction layer over your hardware, which allows you to run like a lot of frameworks. As for example, Spark was originally also like a demo framework to show how easy it is to write frameworks on top of Mesos. And now you can actually run a lot of other frameworks on it, including, which actually a lot of people do, containers. So a lot of people run containers on top of this abstraction layer called Mesos. And they're actually running into some problems sometimes, as for example, out-of-memory exceptions, and then they basically come to us and ask us, hey, why does my container now receive an OOM event? Should be running just fine. My heap space is much, much smaller than the Docker limit I set there. And this is kind of what I motivated this talk, to basically give the answer to what's happening underneath. Why can it happen that those containers receive an OOM? And let's actually get started by containers. So containers, in my opinion, they're a really, really great tool to package stuff. So maybe first to distinguish, like most people, when they hear containers, they think of Docker. So if we're talking about Docker, there are actually multiple pieces to Docker itself. There's the Docker image specification, which basically allows me to specify how a container should look like. Secondly, there's the runtime, so basically the piece of code which actually executes how this container format should be run and isolated on the underlying hardware. And then actually on top, we even have container orchestration now, even in Docker itself, with like this Docker Swarm extension, which made it into like the core product there. So the part I'm talking here about, it's mostly the runtime itself. So how does Docker, or how do also other container technologies, there's not just Docker, there's like Rocket. We actually, inside Mesos, we have our own containerizer, so we can actually run Docker images without having to rely on the Docker runtime. We kind of understand and use the same underlying technologies we're going to explore in this talk to isolate those different tasks. And yeah, we're mostly going to talk about the Docker runtime and how it isolates different tasks / different containers. And actually, this promise that Docker gives me that I can just create my single container, I can create it like on a MacBook, I can create it on a Linux box, and I can actually take the same container specification and run it like on any server I want which is supporting Docker. And this promise for those people working with Java, we actually heard it before in the Java space, and that's also like an interesting connection that both do have this promise, write once and run everywhere. All right, I got to click harder. So, what is actually a container? So, on a high level, it appears like a lightweight virtual machine. I put there an asterisk because it really just appears like that. In my opinion, there's like a huge distinction which we're going to see in a while. So, why does it look like a lightweight virtual machine? It has its own process space, it has its own network interface. I can install packages on that container without influencing any of the other containers running on the same box. I can run services there, I can SSH into it, so it feels a lot like a virtual machine. But if we actually go a level lower, it's something quite different. So it's not like a VM at all. So actually all containers running on the same node, they use the same host kernel. You cannot really like boot Windows or something on there because it basically all relies on like the same kernel. And if you look at it, actually it's just a bunch of processes which are visible also on the host machine. So if I'm on the host machine, I can actually see everything which is going on there. And like in contrast to virtual machines, where I don't see any of the inner processes happening within those virtual machines. So for those people who like it more visual, like the distinction is basically for virtual machines, I replicate the guest operating system multiple times on top, and then I also replicate all the libraries and everything I need. And basically each of those virtual machines, it's its own really isolated operating system. On the other hand, containers, they share the same operating system, and they basically are just different apps packaged together with their dependencies, allowing them to run anywhere. And this is actually, in my opinion, this is like the use case where to use containers for, packaging your application plus its dependencies. I mentioned before, it's simply like a plain process space if I run something. So here I just did a simple experiment. I just ran a Docker image, and then I just checked like what processes are actually running from the host, on the host level. And we can actually see that even though I'm running an Nginx, it's nested under the Docker daemon process group. And it's not running in a separate machine, it's running on the same machine, just nested under those process groups here. Click, click. And yeah, so to summarize or to keep in mind when having to choose what to use, virtual machines or containers. So virtual machines have stronger isolation than containers simply because they all run a different, really different operating system. So imagine I could write some exploit affecting the kernel from within a container. In case of containers, that would really affect the entire machine and also bring down all other instances, all other containers running on the same machine. If I do the same within a virtual machine, I actually just bring down the virtual machine. But on the other hand, therefore, containers have much faster near-native speed for both CPU and I/O, and actually the launch time is also much, much faster, as I'm simply starting a new process with some slight overhead. And also, I don't have the storage overhead for storing like a separate operating system and running a separate operating system for each of my virtual machines. After all, being in the corner, it's all about isolation. If I put someone in the corner, I want to isolate him or her from others as some form of punishment or something else. So let's see what is actually used for this isolation properties. If we look at almost any container technology, this is not just tied to Docker, this is also the same for like Rocket or other technologies. They actually rely on two low-level kernel features. And those are called cgroups and namespaces. So namespaces are actually providing an isolated view onto the underlying operating system. So each process group with its own namespace, it has its own, or it can have its own PID namespace, so it basically can have its own process IDs. It can have its own view onto the network interfaces, IPC, on all the mounts, like it can have its own host name, and also like own user IDs. Control groups, on the other hand, are actually used to both account for things and actually to limit things. So I can monitor and account for CPU shares. I can limit my memory between different process groups. I can limit different net users, and I can also limit access to different devices. So for example, what we do with GPUs, we isolate GPUs by different C groups so that only individual tasks can access them. Let's dig a little deeper into control groups. So control groups, as mentioned before, they're used for resource metering / accounting and actually limiting of the individual subgroups, of the individual types. So I can take care of memory, block I/O, network, and as mentioned, the individual devices. And then there's some kind of like a special C group still. It's called the freezer. Imagine you just want to freeze a task. You want that it receives no CPU shares, no CPU cycles at all. You put it into the freezer, and it's not going to run because it's not going to receive any CPU cycles from the scheduling system. So in general, C groups are really, as most stuff in Linux, really easily built, and you can actually look at it also like in a file system-like manner. So for example, in CoreOS, it's all grouped under sys, file system C group, and there we have the different subsystems. It's the same we saw before. It's like memory, CPU, block I/O, and each of those subsystems has its own hierarchy. And each of those hierarchies actually starts with this root node, and then you can have like a nested hierarchy with the different processes. So each process is represented in there by its process ID, and in each of the subsystems, each process obviously can just occur once, like inside one node, basically. And that actually makes that each node represents a group of processes, like sharing the same resources or having the same limitations, shared limitations onto resources. So we can actually, as mentioned, it's just like a file system, so we can actually look at it. So if we look at that folder, we simply see like all the subsystems hierarchies here. And if we even dig deeper, so if we, for example, look into CPU, we can have those arbitrary names for our subgroups, sub-C groups. And the numbers we're seeing actually there are then the process IDs. And we can actually do the same for memory, and there we can, for example, see that like the database tasks, they are nested under like the database node in this hierarchy, and they'll share all like the same resources or resource limitations. There's actually, this is rather like, can be kind of annoying to look at. And then there's CNIF, container information. It's like a really neat tool written in Go, which you can actually use to look at which C groups are used under a specific namespace. So you can also list all the namespaces, and then you can actually see what we saw before, like how this process running in the namespace is controlled by different C groups from within. So that's really like nice if you want to just check out what's actually happening underneath. Memory C group, accounting. So I can get metrics on almost all of the information I need. I can get swap memory, I can get the total residence set, I can get pages in and out, and actually I can do that for like the individual subgroups here if I need it more fine granular than like the overall memory footprint. More interesting is probably the limitations I can do for memory. So actually each of those groups can have hard or soft limits. Soft limits are actually not enforced, or mostly not enforced, but hard limits, which is actually what most people use, they will actually trigger an OOM killer. So this OOM killer, it can be actually specified, but that's already like the first change if you come from like a Java JVM-based world. You don't get an out-of-memory error, but by default, your task will just be killed as soon as it uses too much memory. And just like as an example, I just choose the Docker example because that's what actually most people use. That would be one example how you can actually set a memory limit for your Fedora image, for example, you're running. CPU cgroup. So again, you can do accounting. You can do accounting per user. You can do accounting for the overall system. But limitations are somehow more difficult compared to memory. So there are two types of limitations you can have. First of all, there are CPU shares, and then there are CPU sets. We'll see what there are in just a second. Click. So CPU shares is actually, it's just like a weight you can assign to different process groups, to different containers, and it's just a relative value. So the default is 1024. So if I would start my Docker image with like a value of 512, that would actually mean that it receives less likely CPU shares as compared to a normal process. More details, so if we actually want to compare two processes, as said, this is relative, so we would start one process or having one C group with a share of 768 and one with 256, then this relative meaning would be that the group A would receive 75% of the CPU cycles, and the C group B would receive 25% of the free CPU cycles across all cores. There's another mechanism to limit my CPU set or CPU usage, and this is actually used to pin task process groups to specific CPUs. So it reserves this CPU for that specific app, and it can also be useful if you have like a NUMA-aware applications or NUMA. So basically, if you have to care about NUMA, that you really want to make sure it's running on CPUs close to each other in this NUMA hierarchy. What actually most people suggest is to use CPU sets rather rarely because it increases the overhead you need to run something in a large distributed system, because you have to keep track who's owning how many real CPUs or which CPUs where. So there's an interesting research paper by Google if you care about the details. Namespaces. Namespaces is the second part. So actually it provides those processes with their own view onto the system. As mentioned before, there are different types of namespaces I can have. And maybe just this one example, the PID namespace, so the process ID, it actually means that within each container, you can have the same process ID, just once per container, but multiple times on an entire host. Like in each namespace, you can basically have the same PID across the entire system. Now let's actually talk a little bit about Java. So Java, similar as Docker, consists of different parts. There's the language, the specification, and then there's the actual runtime. And again, as before, we're going to talk about the specific runtime here. And coming back to the initial motivation why so many people came to us and asked, is like, we should understand what is actually the Java memory impact. Because it's not just the heap, which we or most of us probably specified before. It's much more. There's the JRE memory overhead, there's the perm or now metaspace, the JIT bytecode also needs stuff. If I use J and I, so calling like to native code, I also have an overhead because the objects are actually serialized into memory not managed by the heap. And also Neo also requires some additional memory. It's so fast because it uses like native memory not managed by the heap. And also using threads, each thread basically has to maintain its stack, so it also has to give particular overhead. Just real brief, because that's kind of interesting when using it within containers. Java used to have the perm space, where it's storing like permanent storage, like loaded classes. And now it moved out of this managed heap space. So it's now a separate space within like the native memory space that makes it a little easier to manage from within, and it doesn't cause OOM errors anymore because it's not one of these managed spaces. Before that was actually limited to perm space. Nowadays, by default, if you don't set a specific flag, the meta space will be limited by the entire memory on the machine. So that's also something you should look out for. It's kind of like, it's a potential bug. So if I'm using too much memory, I now don't just screw over my JVM, I'm screwing over the entire system. So that's like a nice use case to have it constrained by a container, because a container will also constrain the meta space used. The JRE actually depends a lot on the core count on the machine to initialize different counts and different metrics. So for example, the compiler threads for the JIT, the default number of garbage collection threads. Of course, you can also override them, but by default, they're just going to be taken by the number of CPU counts, and we're going to see in a second why that matters. So let's bring both sides together, both the container cgroups world and the Java world. And as mentioned before, this information Java uses to determine like the number of threads for garbage collection depends on the number of cores in the system. And that actually recently changed. Like previously, they just used basically the entire number of processors on the system by this variable. And nowadays, they're using scheduler get affinity. And that actually makes a huge difference when running inside a container. Because when you're running within a container, and you have CPU sets specified, it really depends how many cores are being seen by the JRE in this case. So the core assigned, in this case, that refers to Java 9, where we have the, if I go back, the scheduled get affinity. But if we are running on like an older JRE, we actually get the entire number of cores in the system. So imagine you have this huge box standing there, like 32 cores, but your Java only gets, your JE only gets 2 or 3 of them. And then actually this count might be by default having way too many threads for garbage collection and all this other stuff running. So this is something you should be aware of when running Java within a container. With CPU shares, it's the same problem. Basically, runtime get available processes will always return you the entire number of cores on that machine. And as mentioned before, CPU shares should be the default way to use to limit CPU resources. So you should be aware that basically all those metrics the JRE is trying to determine by the number of cores will depend on the entire number of cores on the node, and not like as you maybe try to express here to only use like 50% of the cores present on the system. No, he's going to take like the entire number. And yeah, as mentioned, like if you're on a 32 core box, 32 cores are seen by the machine, and so the default for many settings will be just like 32 threads. How about memory? Memory is actually, it's even harder. So because memory constraints, they are far more problematic because there's no real nice way of querying how that should look like. You should keep in mind this entire Java ecosystem has been developed in a world without considering those cgroups or pooled resources. So Sun, back in those days, they had like zones and this kind of resource pooling, but they actually decided not to care too much about it. And this is kind of like the drawbacks we're seeing right now about it. So there's no real API for the JRE to figure out how much memory it's actually allowed to use. So to conclude, So there are two sides to this. So the good thing about Docker and containers is that it doesn't care about the underlying hardware, what's going on underneath, like a virtual machine would do. In a virtual machine, with all those settings, you would only see the number of cores belonging to that virtual machine, of course. So this has disadvantages we've seen before, just like performance, for example, because I have the overhead of really running this operating system underneath. But it actually also has good things that, yeah, basically the JRE has been written for such kind of systems where it has access to the entire pool of resources it's been given on that machine, and that it's not like subdivided by cgroups, which can lead to then like weird out-of-memory exceptions, because I'm expecting more memory than I actually can use at my convenience, because I'm controlled. All right, that's actually it, and 5 seconds, almost on time. Cool, thank you very much for listening, and that gives us about like 5 minutes for questions.
Excellent. And anybody who has questions, we have 2 mics set up here and here for questions. And just remember, please get close to the mic to be able to pick you up.
Okay.
All right. Well, it looks like there are no questions, so let's give our speaker another round of applause.